Hey, good morning to you all, and welcome back to another episode of Introduction to Computer Networks at NTU. And you know what? Today there's nothing important to announce, so we'll go ahead and dig into the topics. So we have just one video left, which is to talk about the two different implementations of doing client to video server redirection. Okay, so one is to go through the DNS service. The other is to use a dedicated server to do the redirection. So here's the video.
Okay, what's remaining are just two examples of how CDN requests are being redirected such that it reaches the physical location. So in the first example, it's more the Akamai model, which borrows from the services provided by DNS. So example goes like this. Bob requests a video from cinema.com, and this is the video ID. Okay, so browser here, browse around and decided, and Bob here hits this link. But the thing is that that video is actually stored here physically. The King CDN, a CDN company. And so it's stored on kingcdn.com's web servers, this location. But what happens here is, well, Bob's browser actually sees this is the host to contact. So first thing first, ask the local DNS server for the IP address of this guy. Right? So resolve this guy. Bob's DNS server there will what? Check cache. If not a hit, go to the TLD server. TLD server will share what is netcinema.com's authoritative DNS server. And so Bob can direct the query to the authoritative DNS server for the IP addresses of netcinema.com. But what's really curious here is the authoritative DNS server of netcinema.com, instead of returning an IP address, it returns the redirected path. Okay. At this point, Bob's local DNS then resolve for this name instead. Okay. And so check the cache, check with the TLD server, and eventually reaching the King CDN's authoritative DNS server. That query goes, and finally now, King CDN authoritative DNS server will return the IP address of kingcdn.com. Okay, so IP address of this guy acquired, and step 5 sends that IP address back to Bob's web browser. From there, Bob's browser can fetch the video from the actual location of the video. Right, so this is redirecting the client to the copy through the DNS service. In example 2, the content provider here only needs to do the minimum, which is to provide the logging service. So Bob here as a subscriber just logging first. Okay, that's step 1. And quickly, Bob is redirected to the CDN. And in Netflix's case, Amazon's cloud is the CDN. So Bob here will be browsing what videos there are available, okay, and ratings and how long the videos are from the web servers Amazon has already set up. Now, once Bob has decided on watching a video, then step 3, the manifest file of that video is returned back to Bob. And Bob will begin to fetch the video from the physical machine Amazon has set up to store that particular video, and somewhat close to Bob. Last is just that the CDN server begins to dash over HTTP streaming the video. Now if we compare the two models a little bit more, we see that in the first model, the content provider has slightly better control of where the redirections should go. But in the second case, the redirection is all done by Amazon. So there's not much Netflix needs to do, or not much Netflix can do. So it's more a trade-off between control and work. Okay, so more control, more work, less control, but less work. So, well, as a content provider, you'll have to decide for yourself.
All right, so now with chapter 2 done, let's overview chapter 3. Okay, so and the rest of today. So there's going to be a easy part and then the hard part. Okay, the easy part contains the overview of chapter 3 and the very basic functionality in the transport layer, which is what chapter 3 is about, called multiplexing and demultiplexing. That is topic number 3 there. All right, so let's start with the overview. First is you hear Poly breaking down chapter 3, the sections, and introducing the basic terms.
The transport layer. We were at the application layer that's actually higher up. Transport layer, we're getting closer to the heart of the internet. So in the transport layer service, there are a number of important functionalities. Multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Now each of these are important, but multiplexing, demultiplexing, flow control, these two are super simple. They'll be done in like one slide or a couple slides. Now, what's going to take us quite amount of time is this. Reliable data transfer. And then slightly less, congestion control. All right. And both of these functions are implemented in TCP. Reliable transport, congestion control. Now then you can imagine UDP being very simple. All right. It's a connectionless transport layer service versus TCP being connection oriented. So in UDP, you don't need to set up something ahead of time before we send data. But TCP, you need to have a setup process before we begin to send data packets. 3.1 is the overview section. So what I need to say here is this. The transport layer services is actually providing a logical communication channel between the two processes that are running on different end systems. All right. So there's a sender side of the process, sender side of the transport layer protocol, and there's also the receiver side of the transport layer protocol. And the functions is often corresponding each other. Sender side will take messages from the application layer and break it into a number of these smaller segments. And these segments will be passed down further to the network layer. Receiver side is going to take segments from the network layer, reassemble them back to the original message, and that message gets passed up to the application layer. That's when, if this guy here sends an HTTP request, this guy over here receives the HTTP request. So the web server here can begin parsing the HTTP request and then find out what is the object being requested, right? So this is the very basic function of the transport layer protocols. Take messages from application, break it into segments, reassemble segments into message, and pass it back up to the application layer receiver. Now, that breaking of the segments, passing of the segments, and reassembling of the segments are implemented in two different flavors, TCP versus UDP. One is reliable, the other is not.
All right, so that's the basic. Next video, that Polly introduced what the so we just talked about what transport layer does. It's to establish logical communication between processes. The network layer also establish communication, but it's between hosts or machines.
Transport layer versus network layer services. So transport layer there work closely with the application layer. It works also closely with the network layer. But we have not yet talked about network layer functionalities much. So let me just break it to you. What is the main role of these network layer protocols? So what they do is to provide communication between hosts. So meaning enabling sending of messages, sending of packets, or sending of segments through the internet and reaching the other host, the destination, from source host to destination host. Okay, so that is the purpose of network layer protocols. Transport layer, however, is just to establish a logical communication between processes. All right? So between two hosts, there are often multiple processes running. So transport layer handles a pair of processes at a time. So a pair of processes, and network layer handles a pair of hosts. The granularity, okay, of the channel, the entities of the channel are very different. Okay? So transport layer here rely on underlying network layer service. So if there's a process needing to send certain segments to another process, hey, how does the sending process know which way to pass it down further? Because internet is huge and in the middle. That is the network layer protocol's job. So logical connection between the sending transport layer and the receiving transport layer, that is kind of abstract. That's why I keep saying that it's a logical communication, because the network layer is going to handle and find a clear path between the two of them. All right. Now, let me try to use an analogy to explain so that it's more clear the distinction between a transport layer service to a network layer service. So the example is this. Anne here has 12 kids in the house, and Bill has also 12 kids in the house. Yeah, both big families. And for some reason, Ann's kids and Bill kids are good friends to each other, right? So houses there, Ann's house and Bill's house, consider them as hosts. And each kid's generating letters sending to each other will be the processes. So 12 processes generating messages independently, okay, and trying to send them to Bill's houses and therefore reaching Bill's kids. So each letter generated by each kid is an application message. Ann and Bill will then be the transport layer service. So Ann here is the sending side of the transport layer service, taking all the envelopes and then drop it into the mailbox. So it's mixing all the envelopes into the mailbox. Bill, on the other hand, will take all the letters out of the mailbox and distribute each envelope to the destination processes, to each of the kids, right? So Bill there is demultiplexing the envelopes from the mailbox, and there is multiplexing, okay, the envelopes into the mailbox. Now, the mailman, okay, taking all these envelopes from N's box and then go all the way to Bill's mailbox is the network layer protocol. All right, so mailman is the real person there needing to find a way and driving all the way to send all these messages.
All right, so you see that the network layer handles communication to a host, a coarser granularity, when the transport layer handles communication to a particular process running on a host that is finer granularity. So you can imagine in the transport layer, there needs to be a function that's, provides finer grained separations of the messages to different processes. All right. And the last video in the overview is just a quick review of TCP and UDP.
And there are two services again. TCP here does reliable transfer, but it actually does more. Packets are going to arrive in order. Packets, as they get sent, they will also be controlled. So sometimes you can send faster, but sometimes slower. And usually it's when there's congestion, then you send slower. If there's not congestion, TCP sender side will be sending more aggressively. There's also flow control, connection setup. Flow control is such that we do not overwhelm the receiver side buffer. Okay. Connection setup is, if you heard, TCP is a connection-oriented services as well. In order to provide these functionality, reliable transfer, in order delivery, congestion control, and flow control, well, the sender and the receiver side of a TCP connection needs to, communicate a little bit more before setting up a connection. So that takes some time. So there's a connection setup process as well. UDP, on the other hand, is the complete opposite. It's not reliable. It does not guarantee order delivery. So UDP is essentially nothing versus TCP does a lot. So essentially at the transport layer, you have the two extreme of the services. Okay. So it's on top of the network layer, which is called the IP protocol, and it's best ever, meaning do nothing. All right, so no real extension of IP. And so UDP there is very simplistic. Take messages from application, break them into segments, pass it out. Receiver there, grab the segments from network layer, and then try to reassemble them back to the original message and pass it out to the application layer. Now, if there's any segment lost in the middle, that message gets passed up to the receiver side of the application layer protocol. It's not going to make too much sense. All right. Oh, and TCP, UDP, one does reliable transfer congestion control, the other does nothing. None of them provide this delay guarantee, bandwidth guarantee, and none of them provide security guarantee. Okay, and you heard it earlier, the security is provided by this alternative service, but this alternative service is in fact implemented in the what? Application layer.
All right, now let's go ahead and start talking about the first function and the very basic function called multiplexing and demultiplexing. So this video, very brief, 1.5 minutes, but you get a sense already. Multiplexing is to mix the messages, and demultiplexing is to separate the messages so that they go to the right processes.
3.6 multiplexing and demultiplexing. Well, if you still recall the N Bill example, N's kids sending to Bill kids example. N is the multiplexer, and Bill there is the demultiplexer. Right? So if we focus on this example below, so this guy in the middle is a big server machine. There are multiple processes running. You see here, P1 is sending a message out. P2 is also sending a message out. Yeah, the transport layer at the server is doing this, multiplexing. So this host here, from P1 and P2's point of view, generating this message, okay, is the sender. Okay, so sender. So it handles data from multiple sockets or data from multiple processes. Add the transport layer header. So add a little bit more information on top of these packets. Okay. And so therefore, later they can be used for the demuxing purpose. So when messages go out and reaching P3 and P4, and P3, P4 in return generates something back as it arrives back to the server at the transport layer. Yeah, transport layer of the server is going to be working as a multiplexer at the receiving side. And what it does is to look into the header, okay, in these packets, and then decide whether it should be this socket, the message being forwarded to, or this other socket, the message being forwarded to, right? So very simplistic, but very important functionality.
All right. That takes us to quiz 16. Okay, and quiz 16 is asking you this. So let me go to the whiteboard mode. And you see two pictures on the left. Those look like what? Mailboxes. Yeah. And those are the mailboxes of Taiwan's postal system. Those are the boxes to collect incoming mails. Okay. And B, there is a mail lady holding a bunch of letters. Okay. And there's a bunch of mailboxes in a building. So she looks like she is trying to separate these letters into these individual boxes. All right. And let's see. I ask Q1, which device is the multiplexer and which is the demultiplexer? Okay. And Q2, what is on the envelope that allows the demultiplexer to demultiplex? Okay, good. Let's go to channel W7, quiz 16. Okay. Oh, I see. Luis is already providing an answer. Mailbox. Very good. So quiz 16 here. Yeah. I guess you guys are all exercising common sense in some induction. This is good. In the rest of the class, you will see more quizzes like quiz Q16. Before we really talk about how the internet implements this function, I ask something, the same problem, a similar problem from real life. Okay, and based on the common sense and a bit of your engineer's intuition, what is the case? Okay, and in for quiz 16, I think team 13, perfect. Team 9, mailbox is the multiplexer. And you can probably also hear from Polly's description, right? The mailboxes are collecting incoming mails, mixing the mails. And the lady there is trying to distribute the letters into individual units in a building. Okay, so building, coarser granularity, individual household, finer granularity. And the one separating messages from coarser to finer granularity is the demultiplexer. All right. And the address on the envelope is something that allows the mail lady to separate the letters into individual boxes. Very good. All right, so that's essentially multiplexing, demultiplexing. It's a notion that you know well already. Okay, that's the point that I'm trying to prove. Because internet is to communicate digital data. But you see that human beings have mastered communication already. You guys all know how to communicate. So in a way that to communicate digital bits, you can borrow a lot of techniques we use in human communications as well. All right, good. So be more observant of real life And some of these mechanisms that you're using already in real life could be applicable solving communication problems on the internet. Okay, guys? Keep this in mind. And we move on. We're still in multiplexing and demultiplexing. We have not yet talked about how internet or transport layer in the internet does multiplexing, demultiplexing. And this next video is to talk about how. And it's quite brief. Now you know the basic idea. 2 minutes and 20 seconds.
Now back to the lecture. If you think about it a bit more, multiplexing and demultiplexing, which one is more trivial and which one is less? Yeah, multiplexing, just collect the letters and shuffle it into the mailbox, right? No-brainer. But mailman will have to, Bill will have to look at the envelope and see who the envelope is addressed to. So demultiplexing there is less trivial. Similarly, on the internet, the transport layer services receiver also needs additional information, just like names on the envelope, to do demultiplexing. So the information the receiver side of the transport layer service does relies on are these. Okay, the source, destination IP addresses, and the source and destination port number. All right. Now, let me explain. The host that's receiving a packet is going to see this, the IP datagram at the network level. Okay, not quite yet at the transport layer. We are now at the network layer, the receiver's network layer. So what we're seeing there is a packet that we call the IP datagram. So let's call this the datagram. Okay. So now a datagram is composed of the header part and the payload, the data part. Okay, so a header here and data here. Inside the header, there are these fields, the source and the destination IP addresses. Okay, so these information are kept there. So it's a network layer information. And each datagram also carries a transport layer segment, which is this, the data part of the IP datagram. So this here is exactly what's depicted on the side here. It's a segment. Similar to datagram, a segment is also composed of two parts, the headers and the data part. Okay. So the segment's header contains source and the destination port number as well. Right? So source, destination IP together with source, destination port number, they are the information to allow the transport layer services, the receiver side, to do demultiplexing. Okay, I hope this is clear.
All right, so IP address and port number together allows packet demultiplexing. Okay, much like the address on the envelope allows the mail lady to do letter demultiplexing. All right, and there are two ways of doing multiplexing, demultiplexing. One is called the connectionless one, and this is the one implemented in UDP.
And the first form of demultiplexing is called the connectionless demultiplexing. And this is also the kind of demultiplexing being carried out by a UDP connection. All right. So in this type of demultiplexing, we rely only on the destination IP address and destination port number to decide which socket to pass a packet towards. So it's only a two-element tuple. Right? So when a host receives an UDP segment, it checks the destination port number in the segment and then direct the segment to the socket carrying that port number. And that's pretty much it. Okay? Now, of course, the IP address is important because the host at the network layer would be able to decide, whether this particular host is the destination of this packet, therefore keeping the packet and pass it up to the transport layer. And the transport layer could handle this. Yeah, receiving a UDP segment, check the port number, and so on and so forth. All right. So datagrams with different source IP address and different source port numbers, as long as they come to the same IP address, same destination port number, they will be going through the same socket. Okay. So demultiplexing for UDP is slightly simpler. All we care about is the destination address and port number. So here's an example of connectionless demux. So port 9157 is where P3 is sitting on. So that's one of the clients. Port 5775 is process P4 that is sitting on, so that's another client. Server in the middle, open up a port number 642A, and P1 there is the server processing. It's waiting for requests to come in. So we see here a service request message being generated from P3 and intended for P1. You will see source port number being 9157 and the destination port number being the server's port number 642A. And the return messages, so replies from the server will then be carrying the source port number being the server's port number and the destination port number being the sender's port number, the original request sender's port number, 9157, the client's port number. So you see also a little bit that how P1 can generate the reply. The port numbers are essentially the reverse, of the requests. Now, if there's another request coming from P4, what is going to be the source port number? 5775. And destination? The server's port number. And it's probably not hard. The returning messages back to P4, source being 642A, essentially the reverse of these two port numbers.
All right, so the second type of multiplexing, demultiplexing is the connection-oriented. Okay, so connection, let's look at only just the destination IP and port number. But the connection-oriented one looks at both destination and source IP and port number. And this is the one implemented by the TCP.
The slightly more complicated one is the connection-oriented demux. That is also the TCP's demultiplexer. So whether a packet or a segment should go to a particular socket depends on all four information. All right, so receiver uses all four values to direct the segment to the socket. Now, a server process running there on the host could be maintaining multiple sockets for each pair of communication per client. So, for example, a web server, the web processes there could have multiple sockets open for each of the connecting client. And if this is older form of HTTP the web server is running, it could be one socket per object request. Now, let me use an example to illustrate and explain. So we have a scenario where we have three segments being sent from clients over here, A and C, to the server in the middle, B. So all three segments destined to B, and they're supposed to be demuxed in two different sockets. Now, P4 sockets will be using a 4-tuple to decide. And what will be the 4-tuple? Well, source IP address, A, destination IP address, B, and what? Source port number and the destination port number. So these four values is going to be associated with this socket. So when there's a segment arriving at the transport layer, matching the 4-tuple, therefore going to the socket. Similarly, for each of the sockets here and there, the 4-tuples will be stored, and the transport layer looking at the packet header, when there's a match, pass it up to socket to the processes. So that's the idea behind connection-oriented demux. And the reason it's called a connection-oriented demux is because it's not only looking at the destination, it cares also who the sources is. So it's almost like there's a one connection between the source and destination already, the socket. Now, this connection-oriented demux socket is a little bit weird. And this actually happens quite often these days when we're doing this threaded server. So in your PA4, you are implementing a server, all right. What happened there is that you are starting a listening socket, isn't it? Listening socket is a little bit special because no matter where the client is, whatever the source IP is, request coming in, it's gonna be passed to that server socket, that listening socket, all right. Even though, the 4-tuple does not quite match, especially the source IP address and the port number. This type of connection-oriented demux, it is TCP, all right, but it only looks at the destination port number and the destination IP address. Therefore, the message is coming out this way, source being A, source port number 9157. This one here, source being C, port number again different, but then they will all be accepted by the listening socket here.
All right, so multiplexing, demultiplexing, that's the most basic purpose of transport layer protocols. Therefore, both UDP and TCP implements a form of multiplexing, demultiplexing. All right. So UDP, if you heard Polly say that it pretty much does nothing, no reliability and nothing. That's not exactly right. UDP still does multiplexing and demultiplexing. And here's finally more detail about UDP. And towards the end of the video, you'll hear that UDP not just do multiplexing, demultiplexing, but also do something else. That is called checksum. That is to check whether the packet, the bits in the packet, are somehow flipped over the communication channel. You see that human communications can sometimes be lossy in a way that even though you say something, but the listener doesn't necessarily hear entirely what you meant. Okay, so UDP.
UDP stands for User Datagram Protocol. As we've discussed many times, UDP does pretty much nothing on top of the network layer basic service. So we could have segment lost, we could have segments arriving out of order. So no reliability, unreliable. Second characteristic of UDP is this: it's connectionless. Therefore, there's no handshaking, there's no connection setup phase, there's no connection setup delay. As soon as we have data to send, we just generate these UDP segments and push it out. Very low delay. While we have also very low reliability. Right. But hey, some applications would actually like low delay, and it probably doesn't care too much about reliability, then these applications will be perfectly fine using UDP as a transport layer service. So some of the video streaming services, some of the gaming services that we talked about uses UDP. Skype's voice sometimes also uses UDP. DNS, getting the host to IP mapping, we need it as soon as possible. Therefore, UDP here. Now, if one of these DNS query or reply is lost, DNS server, the local DNS server is going to send another request real fast, so don't worry. And SNMP, okay, we have not yet talked about this protocol. It's called the Simple Network Management Protocol. Now, this protocol is talked about in the textbook, but it's in one of the later chapters. Most of the content there is to talk about building a database, defining the format, such that when we measure, for example, round-trip delay from one host to another host, we get to store these round-trip delay data. We get to store packet loss rate data. We get to store available bandwidth measurement data. Right? So SNMP there define these data structure for informations that measures the performance of the internet. SNMP also gets set up across all the machines around the world. If they are enabled, these machines will send these SNMP messages back to the SNMP database. And those messages are sent using UDP because, after all, these informations are nice to have, but they are not really necessary there to ensure the internet continues to operate. It tries to help such that the internet can perform a little bit better. But without these messages, the internet usually works just fine. Right? So those messages are also in UDP. Last point here. UDP does not do reliable transfer, but some applications might need reliable transfer services, but not 100% reliability is required. Then those might add the reliability at the level the application desires, okay, and does application-specific error recovery. So this is one of the reasons people use UDP. Not only because some applications doesn't care about having segment loss, some applications wishes the messages being really fast, and some applications want some level of reliability but not perfect reliability. There's some other use of UDP. Right? So some other advantages of UDP. There's no connection establishment, as we know, low delay. It's very simple. There's no handshake. It's easier to implement. There's also a small header. So this is a UDP segment. Once again, there's a header part. There's also a data part. The header part, very small, just two 30 bits, 64 bits altogether, and that is 8 bytes. Very small header. There's no congestion control, so you can actually blast into the internet as fast as possible. All right. So these are a few other advantages of people using UDP. So there are 4 fields in the header: the source and the destination port number, which we've already talked about. The 2 other fields we have not yet talked about is length. This is the size of the UDP segment entirely, including header and data. And the unit to count the length is byte. Last is the checksum. What's interesting about UDP is that, hey, if you send it out over UDP, there's no guaranteeing of reliable transfer, but you do get this. You get to check whether there's any bit errors in the data part of the UDP packet. And this is the way it works. It's called the UDP checksum.
All right, guys, let me play the next video since that we are talking about UDP checksum already. All right, and before we play the checksum video, you see that in UDP, the protocol, the header part is very simple. Just the source, destination, port number, and then the packet length and the checksum. Okay, very simple protocol. And here's the checksum mechanism real quick, and we'll come back to the questions from Sam and Louise during the video.
This is how it works. At the center side, we take the segment out. Okay, so take the entire segment, including the header, and lay the bits 1 row at a time, and each row 16 bits. So it looks a little bit more like this. Yeah, a row of 16 bits, another row of 16 bits. Okay, so you lay them out and then do what? Summing, okay, of these 16-bit rows. So add them up, and to be precise, it's called the ones complement sum, to be exact. And as a result, you get also a 16-bit output. That is called the UDP checksum. So let's come back here in the example to explain how exactly it's done. So sum, binary add, 0 plus 1 writes 1 here, 1 plus 0 writes 1 here, 1 plus 1 writes 0 here, and carry 1 over here. That's why, even though these 2 are zeros, we still get 1 down here. Okay, just do the binary addition all the way to the end. Now, there could be extra bits being introduced. No worry, what we do in the ones complement sum is to wrap this around and then add back to the number here. So that 1 being added here writes 0, carry 1 over, writes 0, carry 1 over, writes 1 here, and that's the end. All right. Now, the last thing is just to do what? To the complement. All right. So complement is straightforward. Flipping 0 to 1 and flipping 1 to 0. And so in the end, we ended up having the checksum, which is also 16 bits. And this is what's being placed in this part of the UDP segment. All right. So when that UDP segment arrives at the receiver side, receiver does the exact computation, take the segment out, and compute the checksum. That checksum after computation is compared to the checksum field in the packet header, right? If there's no bit error at all, right, the 2 checksums should match, isn't it? So if this equals this, if yes, then there should not be error. But now be careful, there could be specific bit error patterns that the checksum might not detect, okay? So maybe error, but chances is very low. All right. But otherwise, if the checksum do not match, so there's clearly some error. Okay, so application layer there, finding a UDP segment having mismatching checksum can at least discard the packet, discard the segment, knowing that there's already something wrong.
All right, so that's checksum. UDP does check whether there are errors, but UDP does not try to recover from the error. Okay, and let's come back to the questions. Louise had a question about multiplexing, demultiplexing when there are many ports. When there are many ports, when there are more signals that need to be mixed, it will be harder to separate the signals. And so you can imagine for a server, there are probably many processes running or many requests starting processes. In that case, these servers need to run on more powerful machines so that they can handle separations of the messages. There's a question from Sam asking, if demultiplexing judges incoming messages only on the destination address, why there's need of a source port number and why there's need for the receiving process, for the serving process to record the source port number. Well, that is just for the return mail service, return message service. It's not for the multiplexing, demultiplexing purpose. Okay? All right, I hope that's clear. And we move on to the second function of our transport layer, which is one of the major functions we will talk about in chapter 3. That's called reliable data transfer, in short, RDT. Okay. In this first video, let Polly introduce 4 functions or 4 calls that travel between the application layer, transport layer, and network layer. And you can imagine why 4 calls, because there's one to pass data from the application layer to transport layer. There's one from transport layer to network layer. There's one on the receiving side from the network layer to transport layer. And then there's the 4th from the network layer back to the application layer. 4 calls. All right.
All right, 3.4, principles of reliable data transfer. Now, you might see Polly is a little bit more alert talking about this section because this is going to be the most challenging section in chapter 3. And arguably, one of the most challenging section for the entire textbook. All right, so let's talk about reliable data transfer. It's not only challenging, it's also extremely important. All right. So it's not only important at the transport layer, some of the link layer services might also implement some level of reliable data transfer. At the application layer, someone might be using UDP as the underlying transport layer service and implement its own reliable data transfer. So maybe it'll be more efficient than TCP instead of using the native TCP provided in the protocol stack. All right. So it's one of the top problems when one needs to design a communication network. Now this is the setting. We have processes sitting at the application layer. Okay. There's application layer protocol, but there's also transport layer services. These processes depend on to transfer application level messages. So sending processes here, sending out data. Data will go through a channel. Now this is reliable data transfer service, so the channel is reliable. And hopefully at the other end, the receiving process grabs the data and then interpret the data and things will just work out. Okay. But the thing is, the internet is not exactly reliable, isn't it? So yeah, we do have unreliable channel when packet goes through the internet infrastructure. Now, but application, sending process, receiving process are demanding reliable transfer. So transport layer service here, the sending side and the receiving side each will need to implement some extra mechanism to ensure somehow lost segment is recovered, somehow the flipped bits are corrected. Right? So that is RDT. Okay, and we're going to go through a few generations of these RDTs and show you how the sending side is implemented, how the receiving sides can be implemented such that we provide such an illusion to the application level services. Oh, and by the way, it really depends on how unreliable the channel is underlying. Then the complexity of the reliable data transfer can vary. Very unreliable, very complicated. Not that unreliable, then slightly simpler. Now, we'll be using these notations, RDT send, UDT send, and all these throughout the discussion, introducing you generations of these reliable data transfer protocols. So let me blow it up and explain a little bit further. All right, so sending processes here, generating messages. Those messages get passed down to the transport layer. And those messages are now called data. All right, and RDT send is the function called the sending process calls to pass the data down. Okay, so let me bring it up. RDT send here is to be called from above, from the sending process. Okay, and it is to pass the data down such that it will arrive at the receiver end. Good. Well, and these messages is going to be processed here, and a number of these segments will be generated, or packets will be generated. So when we're talking about generally reliable data protocol design, let's just call these packets. Okay, so messages now data, segments is now packet. And the action of pushing the packets down to the unreliable channel is UDT send. Okay, UDT send. So UDT send here is call by the RDT, the protocol sending side, to transfer packets over the unreliable channel. All right. And then, data is going to travel through the channel and come to the network layer. So that network layer component would call this, RDT receive, to pass the packet further up. So packets gets passed down by calling UDT send. Packets gets passed up, by calling RDT receive. And this is called from below, from the network layer, when packet arrives. And those packets will be processed here, and then the receiver side of the transport layer protocol is going to call yet another one, receiver data function. So this is called by RDT, the receiver side, to deliver data to the receiving process above. So data here is going to be passed above. So 4 function calls to refer to actions. First, coming from the sending process to the sending RDT. Second, from the sending RDT to the unreliable channel. Third, from the network layer to the receiving RDT. And the fourth, from the receiving RDT back up to the receiving process.
All right, now you know application send, RDT send, UDT send, UDT receive, and deliver data. These 4 function calls meant. All right. Now there's another video. In that video, you will see that in addition to the introduction of these 4 function calls, we'll also introduce the finite state machine system. We'll use that to describe the mechanism of RDTs. And as you can see in the topic slide here, we'll gradually introduce more and more complex RDTs. And throughout the process, we'll use the finite state machine with these 4 function calls. So let me introduce the finite state machine system.
Now, we'll try to describe generations of these reliable data transfer protocols. As Polly mentioned slightly earlier, these various generations, one is simpler, second slightly more complicated, third even more complicated. So they go from simpler RDTs to more complicated RDT. That's because we assume the underlying channel being more reliable to less reliable, to very, very general, like the internet. All right. So that is just to prepare you for the RDTs that we need to introduce coming ahead. Now, another thing that I need to introduce is how I'm going to describe these RDT mechanisms. We're going to use, this thing called the finite state machines. Finite state machines, FSM. So here's one state, here's another state, 2 states. So finite number of states. So this is a machine to go from one state to another station, from one state to another state. You might have a transition saying that under this condition, then we go from state 1 to state 2. And in the meantime, we transit from one state to another, we take this action. So the arc here defines when will a machine jump from one state to another, and what is the action to be taken corresponding to this event occurring. So at each state, there could be number of events, that could trigger the state changes, and that could also trigger additional actions to be taken. So provided a machine, a mechanism, usually engineers can describe the mechanism using a finite state machine like this. All right. So FSM is also, if you recall, formal method, finite automata. When you're taking these courses, finite state machine is a notation that you should be familiar with, because it's a way to describe a computational machine. And it's to describe it in a more formal way. Provided the machine, then the implementation will be straightforward. It's a little bit like when you take an algorithm course. After you learn how to write a pseudocode correctly, provided the pseudocode, your programmer that you hire will be able to program. That is the only thing that's required to communicate to the programmers. Oh, there's one more thing I neglected to mention. Yes, we only consider a unidirectional data transfer. So what I meant there is that one machine to another machine, data is going one way, and there's no data coming back. So data go, receiver, and receiver might send feedback back. Those are called the control info. Okay, control info can go both ways, but data only go from the sender to the receiver.
All right, good. Yeah, I know some of you are a little bit concerned whether you'll be able to understand the mechanism described using these finite state machines. No worries, we're going to start from the easiest mechanism, RDT 1.0, after the break. So it's now 11:10. We'll resume the lecture 11:20. In the meantime, Luis, I think it's relatively speaking between UDP and TCP. TCP is still slower. Now, whether the loss and delay will be unbearable, it really depends on the nature of that machine. If it's a server, it can be unbearable. But usually for people hosting a server, they would try to acquire hardware or enough memory space to make sure that the operation is smooth. All right, I hope that answers your question, and break begins. Let's return 11:20. All right. It's almost 11:20. Here's just to remind you again, finite state machine system. You see that in such a system, when there's a certain set of actions to be taken, what do? You check the starting state or the current state, right? And there's an event occurring because among the transitions that points out of the current state, which one you trigger depends on the event. Okay, so check for the matching event and take that transition and you move from the current state to the next state. As you do that, there's a bunch of actions you need to take in the meantime, typically. So that's what the finite state machine defines. For complicated mechanisms, you get lots of these states. And for each state, there could be multiple transitions to take, multiple options to choose from. Okay, good. Now, let's check out RDT 1.0. This one is trivial. This is assuming that the underlying network channel is reliable. Therefore, the sender just send packet, receiver just receive packet, and that's all they do.
And now RDT 1.0, the generation number 1. Right? So in this generation, the assumption is very strong. We're simply assuming that the underlying channel is reliable. As a result, sending side of RDT, receiving side of RDT, there's nothing really needs to be done. So the machine is very simple. So this RDT 1.0 is just so that you are more familiar with the finite state machine notation, right? So underlying channel is perfect. No bit error, no lost packets. Okay, so the sender side of the finite state machine, FSM, will look just like this. Okay, so there is always at least one state that is also the starting state. There's no ending state for these machines because they'll be looping forever. Okay, so starting state is wait for call from above. Okay, so application calling data to be sent to the transport layer. So calling from application from the sending process is RDT send, isn't it? So when you run into this event, the sender there will generate packet out of data. So data is the thing coming from the application. And packet is generated to be pushed out. And to push down, we call UDT send. All right? So this is the FSM at the sender side. Similarly, at the receiver side, call from below. Right, so when that is happening, RDT receive being called, receiver side of the RDT 1.0 will just extract data out of the packet and deliver the data up to the application layer. All right, so again, events triggering changing of state, and the arc direction indicates which state it changes to. And so a loop coming back is saying that, hey, we stay at the same state. Right? In the meantime, we take these actions. So event triggering the transition. In the meantime, we make the transition take these actions. So you see, sender side keep being triggered from the application, calling this and triggering actions to occur, triggering the state being changed. So that is the general idea of FSM and using it to denote a functioning machine. All right. Sender sends data into the underlying channel. receiver sends data from underlying channel here. All right.
All right, so that was RDT 1.0. You see the 4 calls very important because you see at the sender side. There's RDT send, right? That is the triggering event. And then the data passed down to the transport layer. What does the transport layer does? Action number 1 is take the data, make a packet out of it, right? And then that packet calls the UDT send to pass down to the network layer. At the receiving end, UDT receive, and the receiving end transport layer is what? Extracting data out of the packet. Extract. See, there's another function called being added, but it meant to take the data out of packet and then pass the data up, deliver data to the application layer. Okay, so I hope that you are fine with all these new notations. Now let's move on to a real RDT where there are errors. And this time we assume just the simple form of error having some bit errors. So that makes that RDT version 2.0, handling bit errors. And here's the idea.
And then RDT 2.0. So this is when the channel is no longer perfect, but it's not so bad either. We do have some problem, but just this problem, having bit errors, meaning the packets, okay, if you look inside, some of the bits might be flipped. Therefore, it failed passing the checksum at the receiver. So the computed checksum and the packet header checksum somehow didn't match. Receiver then detect bit error. The question is, how do we recover from this error? Well, you know, if you're thinking how to do this in the computer in the transport layer, I'm sure that's very hard. But if you think this, how do humans recover from errors during conversation? Say, if Polly was trying to describe finite state machine and it sounded really fuzzy to you, what would you do? There you go, right? You type up in the live chat and ask, hey, what do you mean transition? What do you mean changing from state to another state? What do you mean a certain event occur and triggering the changing of the state? It's not clear. And Polly then will try to explain again. Now you retransmit the packet again. So, sure, if you abstract this exchange of feedback and data and retransmission, you see the general idea seems to be receiver upon detecting error, sending feedback to the sender, sender retransmit the packet again, and hopefully the second time it's clear, no longer fuzzy. That is the general idea of RDT 2.0. So to describe RDT 2.0 a bit more formally, those feedback you're providing to me, in the computer system, they'll be either in this form or this form. So acknowledgement there is a positive feedback. Negative acknowledgements, therefore, the negative feedback. Acknowledgements there or acts there are to explicitly telling the sender everything is all right. And next here is to tell the sender, something's wrong, and therefore the sender can retransmit the packet. Okay, so retransmit of the packet is triggered by the receiving of next. This is exactly what's defined in RDT 2.0. So let me stress, there's first, detecting error. Second, sending back of the feedback from the receiver. And then retransmission of packet coming from the sender in case negative acknowledgement is received.
All right, so the mechanism is simple, having the receiver sending some sort of feedback back to the sender, and so the sender can try to retransmit if it's necessary. But that's in human language. I think the next video, this one is long, 5 minutes, that's describe that mechanism in the finite state machine system.
Now, what's a little bit harder is to go over RDT 2.0's finite state machine. All right. Now, try to be a bit patient here. Let's focus on the sender side of the FSM first. This time we do have 2 states. One is wait for call from above. Oh, okay, this one is familiar, right? So this is the initial state. The sender is waiting for the application process to send data down to the transport layer. Okay, so wait for call from above. And there's going to be a transition triggered by this event, RDT send, the application calling and having data to send. The sender here, transport layer, will then create packets from data. And this time, in order to detect error, we need to add the checksum. All right? So, hey, this is very abstract, but you get the idea. When you're generating the packet, we do need the data from the application layer, but we also need to compute the checksum. All right, so when we generate the segment, make sure that the checksum is somewhere in the header. Very good. So send packet is finally generated. So this is the segment. And sending side of the transport layer service calls UDT send to send the segment out through the underlying channel, right? And that also take the sender from the wait for call from above state to the what? Wait for ACK or NAG state. Oh yeah, so after we send the data out, then we'll be waiting for feedback from the receiver. Good, makes sense. All right. Now, hey, here, what's coming back as feedback could be positive and negative. So therefore, you see two transitions possible, one over here and the other over here. So this is the negative feedback case, and this is the positive feedback case. Now, the easier one is if the feedback coming back is positive, right? So this is when the sender receives a message back from the network layer, so it needs to be triggered by call from below, RDT receive, the receive packet. And you check whether the receive packet is positive. So if both conditions true, then hey, do nothing. So this is empty set, do nothing, and then return to wait for call from above state. Meaning, hey, positive feedback, so move on with the lecture, for example, so to speak. Right? So, hey, Polly can actually teach more next. But if the feedback is negative, so if some of you say, hey, wait, no, not clear. Can you do this again? Can you talk about it again? Well, in that case, okay, RDT receive called and the feedback is negative, what? Yeah, Polly resend the packet. So UDT send, the packet that's generated being sent already once will be, yeah, sent once again. Okay, so it's a retransmission. Now, what's a bit interesting is this. When we're at the wait for ACK/NAG state, when we receive a negative feedback, we actually come back here again to wait for feedback. So hopefully the next one is going to be acknowledgement, and therefore we can leave the waiting for feedback state. Right? So that was sender side of RDT 2.0, the finite state machine. Now let's move to the receiver side. All right. Whew, there's only one state, cool. But there are two different transitions, one above, the other below. So they are both triggered by RDT receive. So receiver there would be, call from below from the network layer saying that network layer, I'm here and I got the segment for you. I got a datagram for you. All right. And then you grab the datagram, remove the IP header, and you see the segment. You try to do the checksum computation, isn't it? Right? And there are two different conditions. One is if the packet does have bit error, meaning the packet is corrupted. Then you need to do what? Send the negative feedback. So UDT send. So UDT send is what? To send the data down to the network layer. And so receiver there sending the data down to the network layer. Network layer is going to send it back to the sender. So UDT send NAC is the action being triggered. And receiver comes back to wait for call from below. So it could be a correct data packet. It could be an incorrect data packet, depending on which is the case. So incorrect calls this arc. Correct calls this arc. If it's not corrupted, extract the packet. Okay, extract the data out of the packet, deliver the data up to the receiving process, okay, and then send back positive acknowledgement. All right. So sending feedback, sending feedback. But if everything is correct, the receiving part of the transport layer, receiving part of RDT 2.0 is yet to extract data and pass it further up to the application layer.
All right, so you see, the sender side now, after sending the data, will stop and wait for feedback, ACK or NAG. And so from that state waiting for feedback, there could be ACK received, therefore you move on, or NAG receive, retransmit. So that's how you describe the mechanism in human language in a finite state machine, the sender side. The receiver side is slightly simpler. The change is just that after getting the packet from the network, UDT receive, we extract data out of the packet, but you check whether the data is corrupted. In case it's corrupted, you take the arc, the transition above, otherwise below. But in both cases, we send some sort of feedback back to the sender. So in the upper arc, it's a negative acknowledgement. The lower arc, positive acknowledgement. Okay, the receiver does not stop and wait. Okay, the sender side obviously does stop and wait until feedback is back. And until it's positive, then you go back to the waiting for data calls from above, waiting for RDT send to send the next packet. Okay, so this kind of finite state machine, this kind of RDT is also called the stop and wait type of RDT. All right. Now, no worries. Let's check out a couple examples. The first example, straightforward, no error. Second example, with bit error. Let's go through these two examples and see if you can accept, okay, describing mechanisms in finite state machine better.
Okay, now let's walk through a couple examples to show you how the sending side and the receiving side of RDT interacts. Okay, so this is RDT 2.0. And this is an example showing that, hey, there's no bit error in the packets. So, originally, okay, the sender starts from the initial state, wait for call from above. Receiver here also, starting here, wait for call from below. All right, so now we get a call from above. Okay, RDT send being called from the application layer, the sending process. Now, sender side would actually take the data, add the checksum, and create a packet, send packet, and then call the UDT send to send it out. All right, so go through that, and that packet is going to arrive at the receiver end. Receiver side of RDT 2.0 will be called. Okay, but there's no error. Okay, so this is the no error case, so it's going to pass this condition, receiving a packet from below, and it's not corrupted, therefore triggering these actions being taken. Data extracted out of the receive packet, delivered to the receiving process, and sent back in positive acknowledgement. So let me remove the notes. Yeah, so we'll be triggering this transition and all these actions, and that message is going to come back here. Okay, so you see it flashes, but essentially we were waiting here, right? And that packet, egg packet, is true. Therefore, both together is true. And we do nothing and simply return to wait for call from above. So this is the case between the interactions of the sender, RDT 2.0, and the receiver, RDT 2.0. Okay, let's do it again. Oops. Okay. At the beginning, here, starting state, here. Sender gets called from above, triggering these actions, taking a transition, and message is going to reach receiver here. Okay, and it matches this condition. Therefore, these are going to be triggered, and we stay in the wait for call from below state. And this is going to generate a message being sent back this way. Yeah, and because it's an ACK, therefore we trigger this transition, and the sender goes back to wait for call from above state. All right, so this is the no error example. The next example is more interesting, where there is error. All right, so similarly, sender starting from wait for call from above state, receiver starts from the wait for call from below state. And yeah, there's a call coming in. Okay, generating the packet, send the packet out through the network layer. Straightforward. So this event match and these actions taken, and we take the transition and move to the wait for ACK or NACK state. And that's going to generate a packet to the receiver. And this time, yeah, this event is triggered. Network layer says I have a packet for you. And which of the condition matches? Well, we have error here this time, so it's corrupt. Therefore, we trigger this transition to occur. Condition match and this action, and then stay in the same state. So we're calling UDT send, and we are sending a negative feedback, the NACK. That's going to fly back. So sender here waiting in the ACK, waiting for ACK or NACK state, then gets a call from below. And it's checking and finds that it's a NACK, not the ACK. Therefore, this transition matches and being triggered. This action is being taken. So UDT send packet is what? Retransmission of the send packet generated earlier. Okay, and sender here stay in the wait for ACK or NACK state. So this is taken and packets being sent again. But the second time, yeah, we're lucky. Second time it's not corrupted, therefore we trigger this transition and another packet being sent back. And this transition now, because of the condition being matching, yeah, we do nothing and we return. The sender returns to wait for call from above state. All right, should we do it again? Oh, probably not, right? You get the idea. Okay, so the interaction between the sending and the receiving machines of RDT 2.0, how they interact. Okay, so there are actions being triggered, and in the meantime, packets being generated, and they would go to the other end, and feedback being generated, coming back to the other end.
All right, so that two examples should make it a little bit more clear how you read the finite state machines. Now we go on to 2.1. That's because 2.0 is problematic. One of the issues pointed out by Sherman is, what if the ACK-NACK coming back from the receiver to sender is somehow lost, right? Would the sender side get stuck? Yes, it gets stuck. It will be in the wait for ACK-NACK state forever. That's another issue that we will address next week. But 2.1 is to address another issue. What if we have bit errors in the NACK ACK coming back to the sender? Have you thought about that?
But RDT 2.0 has a fatal flaw. Yeah. If data can be corrupted, therefore a receiver needs to send ACK and NACK to provide feedback to the sender. The ACK and NACK coming from the receiver to the sender, those packets can also be corrupted. So what if that feedback packet is corrupted? Then sender will not know whether it's really an ACK or a NACK. So should the sender retransmit, or should the sender say, okay, I'm just gonna wait for another call from above? Dilemma. So what do we do with this? If you think a little bit further or recall back, didn't we have the same situation, right? So when data is corrupted, we ask the other end to send feedback. So perhaps we could ask the sender of the data to send feedback so that the receiver will know whether the ACK or NACK is corrupted, therefore retransmit the ACK or retransmit the NACK. Yeah. So how did we deal with the corrupted data? We do the checksum, right? At the receiver. Well, actually, we do the checksum at the sender, adding that into the packet, and receiver check it again. Now, if it's not a match, we send NACK. If it's a match, we send ACK. So this is receiver side action. And therefore, at the sender side, we could retransmit data. So perhaps we will do this, right? So ACK, NACK corrupted. There's potential. So why don't we do checksum, okay, on the ACK, NACK? So receiver there adds checksum for the ACK, NACK. Sender there checks if the checksum matches. And sender, upon seeing a mismatch, sends a NACK for the ACK or NACK. If it's a match, sends an ACK for the ACK or NACK. Therefore, data receiver there can retransmit the ACK and NACK. Oh, makes sense. But if you think a little bit further, how do we ensure that the ACK-NACK for the ACK-NACK is going to arrive back at the receiver, right? What if these guys are corrupted and therefore the receiver will not be able to tell whether the former ACK-NACK being sent is corrupted or not? Exactly. What happens if the ACK-NACK of the ACK-NACK gets corrupted? Okay, so you have circular dependency there, and the problem never gets solved. So alternative thinking coming next. The new thinking to address the circular dependency we saw earlier is this. The sender, okay, will just not figure it out, okay, whether it's ACK or NACK being corrupted, okay? So sender will just pretend to be dumb and not trying to ask for a clear answer. Sender here instead retransmit the data that's already sent to the receiver. Would that work? If the corrupted ACK-NACK is a NACK, then hey, this addressed the issue, isn't it? If the corrupted feedback is an ACK, then this actually creates duplicates. So the receiver side, in case it being an ACK feedback being corrupted, might have duplicate data. So this is actually not good because at the receiver side, it's going to receive segments one after another, and it's just going to reassemble everything and then pass it up to the receiving process. If that's the case, you might see typos, duplicated sentences, duplicated phrases here, there in the document, or sometimes duplicated pictures or partial pictures. Okay. So in RDT 2.1, to really seriously addressing the issue, we need to add a sequence number to the packet sent so that the receiver side can check the sequence number and see if the packet that has already been received earlier matches the sequence number that I'm receiving now, the receiver is receiving now. If they match, then that is very likely a duplicate from the sender, okay? And the corrupted feedback is an ACK. Okay. So entirely in RDT 2.0, sender will just retransmit the current packet in case the feedback is corrupted. But in the packet, it's going to carry a sequence number that will allow the receiver to tell whether this is a duplicate or not. In case the receiver detects it's a duplicate, it would scar the duplicated packet. And this is RDT 2.1. And there's one more thing we need to talk about. That tells a little bit about the sequence number requirement here. Think a little bit more. RDT 2.0, RDT 2.1. The sender behaves this way. After sending one data packet, it's going to stop and wait for feedback until everything is cleared. Then it will go back to send data again. So sender sends one packet and it's going to wait for feedback until everything is cleared and move on. So you see, if the receiver during the phase in stop and wait state receiving two packets carrying the same sequence number, then that must be a duplicate due to a corrupted ACK, isn't it? Yeah, so sequence number in such form of reliable data transfer is very simple. It needs only one bit, two numbers, 0 and 1, to tell whether it's a duplicate apart from a new packet.
All right, so we add a sequence number to check whether it's a duplicate or not. Okay, so retransmit anyway from the sender side. And the receiver here depends on the sequence number. And sender back will check also sequence number of the ACK. And so next is the finite state machine. Okay, and because things get complicated really quick, because when we add one bit of sequence number, then we have two sequence numbers. So the same set of states and transitions will need to be duplicated for another sequence number. So you see that the number of states quickly doubled, okay, when the sequence number is one bit. But good thing is that, yeah, although the states are doubled, but it's symmetric because the actions to be taken are the same. Okay, so let's check out the sender side. It looks complicated, but in a sense, it's symmetric. Okay, one half is the same as the other.
Now, judging from the description, it sounded somewhat easy, not that complicated. But if we look at the finite state machine, it looks somewhat complicated. And you know what? This is only the sender side of the FSM. We have not yet looked at the receiver side, all right? So this is the sender side of RDT 2.1, which is the version of reliable data transfer that handles corrupted ACK coming back from the receiver. Now, the easiest way to look at the finite state machine here is by drawing a line separating the two mirror parts. So if you look at the upper right part of it, this looks like the wait for call from above state in RDT 2.0 sender, isn't it? And wait for ACK, this looks like the waiting for feedback state in RDT 2.0 sender. If you go down further, this other half, it's actually very similar. Wait for call from above, and then wait for ACK. Okay, the only difference is this. Wait for call for packet 0 from above versus wait for call for packet 1 from above. We just talked about the sequence number required to separate two packets one after another. from a duplicate, a retransmission of an existing packet, isn't it? So having 0 and 1 is a way to tell duplicate packet apart from a fresh packet. So we do need to have the separation here in RDT 2.1 sender. And as a result, when we get a call from above, so application calls RDT send data, we'll then trigger these actions to occur. So we'll be making packets, taking data, and we do the checksum, right? So this is in order for the receiver to check and see if the receiver sends ACK or NACK. The new thing we add here is, to add sequence number to the packet we're creating. So the send packet here now contains not just data, not just checksum, but also a sequence number. And as usual, we send it out through the network layer. So we call at the transport layer called UDT send. Now, the second thing that is a bit unusual is also this. Hey, the feedback state, wait for feedback state, you see, wow, the condition looks all complicated. Particularly if you see, we're now checking first whether the feedback we receive is corrupted or not, whether it's actually intact or not. So this is the case when it's corrupted. This is the case when it's not corrupted. So if we receive a packet from the network layer, receive a feedback packet from the network layer, and we check that it's not corrupted, everything is fine. And that packet is a positive feedback. That means what? Transmission of packet 0, perfect. So we do nothing and then we move on to wait for call from above again. All right. So this transition here is straightforward. Now, what is a little bit unstraightforward is this transition. So this is the transition that we come back to wait for feedback again. Okay, so these are the complicated cases. You see here, if the ACK or NACK coming back is corrupted, what do we do in RDT 2.1? We'll just retransmit the packet that's sent once earlier, isn't it? So if it's corrupted, simply send it again. So the send packet here is not actually being reassigned. So it will be the packet we have sent earlier. So it will be carrying sequence number 0. There's another condition. If the packet is not corrupted, but it is a negative acknowledgement, then it's just like in RDT 2.0, we retransmit. All right, so this transition here gets, doubled. It's checking two conditions. If it's not corrupted, a negative acknowledgement, retransmit. If it's corrupted, also retransmit. So we have two conditions that actually ended up doing the same thing, just retransmit. All right. And so that is the sender side of RDT 2.1, and we'll just not cover the rest of it because it's pretty much the mirror. Okay. The only difference is just that handling data packet 0 versus data packet 1.
All right, so that was the sender's finite state machine, right? As you follow the video, you see that the upper right is essentially the finite state machine of 2.0. Lower left is just the same thing, except that the upper right is handling sequence number 0, lower right handling sequence number 1. And now let's check out the receiver side. It's also double, but symmetric again.
And this is the receiver of RDT 2.1. You see similarly the number of states and transitions also doubled. We borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right still are the mirror of each other. The difference is just that the upper left is handling data sequence number 0, expecting data sequence number 0, and the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACK/NACK corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering, this condition, this transition. Okay. So receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0, perfect. Let's extract the data, pass it up to the application layer, generate the ACK packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACK/NACK could be corrupted. So checksum here is to enable the data center to be able to check whether the ACK packet or the NACK packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition, receiver here, go back to, wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below. And this will go on and on and on and on and on. And when there's no data corruption, when there's no ACK-NACK corruption. Now, what if there's data corruption in RDT 2.0? Yeah, that's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. Generate a negative acknowledgement, but hey, in RDT 2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the NACK, send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT 2.0. The two transitions remaining, yeah, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay? That's when the sender retransmit sequence 1, thinking, hey, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. All right? So if that's a duplicate, no, that's not extract packet, that's not deliver, again, the same thing out to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, yeah, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and then can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So, yeah, this is RDT 2.1.
All right. Okay, before we go through an example, so there were a couple questions. One from Sam asking, what if the sequence number bit is flipped? Okay, and if that bit is flipped and the internet checksum did not detect that, yes, RDT 2.1 might result in receiving duplicate data. All right. And can the internet checksum not detecting some some error patterns? Yes, because if you think about it, right, what it does is to shrink whatever size data messages are to just 16 bits. So you kind of compress the information, higher amount of information to something that's much smaller. Okay, so certain patterns of error bits might not get detected, but the chance is very rare because it needs to be a high number of bits making errors at the same times and in a certain pattern. Okay, so very rare. But in case that happen, we might get duplicate data. Good. Now let's walk through an example to exercise RDT 2.1. Right after that, we'll go through quiz 17. And quiz 18 there is actually a pair with quiz 17, but let's make 18 a take-home quiz. Okay, so it's there only for you to exercise more RDT 2.1 with some ears. Good, so let's play the example, and I'm gonna take the fast responders for bonus with quiz 17.
Now let's use a couple of very simple scenarios to demonstrate how the sender and the receiver interact. So this is our RDT 2.1, no error case, and scenario is simply first to send one packet, and then second, continue and send yet another packet. Okay. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is that send one packet. Now, we're here at the starting state to determine what transitions to take. Let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send one packet. So obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's going to complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for ACK or NACK 0 state. Right? So very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event. And then take the actions, and then finish the transition, and land on the ending state. All right, so let me repeat, starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side, currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all three of them starts from the state here. Now, event is, yeah, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no error, so this one is not possible. So this one passed to this point, this one passed to this point. But there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0. Therefore, eventually, this transition waits. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state. Wait for 1 from below. And now next, right over here, the receiver is generating an ACK packet and it's being sent back. So that's gonna trigger an ACK packet arriving back at the sender. So sender here currently at the wait for ACK or NACK 0 state. See, there are 2 possible transitions. So which of these matches the ACK packet with no error? Yeah, this one here. No error, and it's ACK packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to this state. And there's nothing to be done here. No more packet being generated flying back to the receiver. So we could have stabilized this right here. So sender here, stop here. Receiver, stop here. Okay. And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side.
And that takes us to quiz 17. But you might see here that we're supposed to go through scenario 2 because we just went through scenario 1. You know what? Scenario 2 is pretty much the same. And so we take pretty much the transition on the other side. You see that it's symmetric, right? T3, T12, and T4. Now, quiz 17 is asking, now let's consider bit errors. And so scenario 3 is for quiz 17. If we send a packet and there's a bit error, but there are no more bit errors afterwards. So it's just that when we call T1, we send the packet, but there is a bit error in that packet. So it comes to the sender, to the receiver side. Then we need to check 3 transitions and see which event, which transition matches the event that is supposed to happen based on the description here. Okay, good. And let's go to the discourse phase. I see you guys are picking up this really well. Good for you. And yeah, you guys are all correct. T1, T15, T5, T11, and T2. Very good. And so here's a quick animation. You see that from sender and receiver starting state being wave for call 0 from above, and the receiver wave for 0 from below. You see the first event is RDT send, therefore triggering the T1. And the ending state after that transition is wave for ACNAC 0. Okay, and that packet gets sent to the receiver. Receiver would check, and it's corrupted this time. Therefore, we take transition 15, right? As a result, we send a NAC packet, and it will go back to the sender. Sender currently in the wave for ACNAC state, right? And we check the condition. There's no more bit errors. Therefore, it's not corrupted. So we take what? Okay. It's not corrupted, but it's a NAC. So we still pass T5. Good. You guys are good. Okay. And that data is retransmitted. Packet 0 is retransmitted. And you see that the sender here, wave for 0 from below, checks whether it's T11, T15, T16 being called. And this time, no bit error and sequence number 0. So we take T11, right? And a real ACK is sent back. And now it's no corruption, and it's an ACK. Therefore, we take T2. And both finite state machine stabilizes. Okay? And so, again, it's T1, T15, T5, T11, and T2. Perfect, guys. So exercise one more time with quiz W7, quiz 18. So let's go to the score space. Yeah, there you go. So you guys did really well, quiz 18. So quiz 17. Quiz 18 is take home. So if you can spend a couple minutes later after the class. Oh, okay, really fast. You know what? Team 2, I'm not sure if it's exactly right. Careful, careful. We are now in wave for 1 from below because quiz 18 is to continue from quiz 17. So the starting state for the sender is actually wave for call. So the starting state will be here for the sender, right? And here for the receiver. Right, so after receiving that packet from sender 1, okay, with bit error, whatever transition trigger should be 13, 14, 12, right? One more packet, but there's a bit error in the returned. So no corruption, no corrupt. has sequence number 1. Oh, okay, you're correct. It's T12. Yeah, I actually made an error. Okay, perfect. And then T6. Ah, team 2, Henderson. Very good. Polly's solution is not exactly correct. Okay, very good. All right, so that's quiz 18. All right, so feel free to take some time to work on it after the lecture. But with that said, that ends the lecture today. We finished talking about RDT 2.1. Next Tuesday, we're going to play a summary video of RDT 2.1 and set the stage to go on with RDT 2.2. Okay, and eventually RDT 3.0. RDT 3.0 is the version that addresses Sherman's question. What if, because in RDT 2. something, we assume bit errors. We did not assume packet losses. What if we have packet drops entirely? Okay, so the ACK and NACS might not come back, or the data might not come to the receiver. Okay, how do we handle that? That's going to be in RDT 3.0. All right. So with that said, that's all the time we have this week, and I'll see you next week. Goodbye. Bye. Sure. It's okay. Take your time with quiz 18. All right. And just so you guys know, when I meant fast responder, it's not necessarily the fastest, okay? Because you guys kind of all answer within like a window of like a few 10 seconds. That's equally fast. So these are all taken as fast responses. Okay. So I'm just gonna place a tag here to separate the fast responders from the slightly slower responders. Okay.